they are making claims that are dishonest. They are telling people that this is measuring biological age. It's not. It's a correlation to biological age. And so people are being misled, and that's problematic. Where I really, though, see a problem right now is when medical providers, physicians, longevity docs are recommending these biological age tests. To me, that is irresponsible. This is a provocative word, and I don't mean malpractice in the sense they should be sued for malpractice, but that's medical malpractice. A medical provider, in my view, should never use a test, number one, they don't understand. A few docs understand these tests, the vast majority don't. You should never use a test where you don't know the precision or the accuracy of the test, or at least you can find that information if you need to know it, right? We have no idea what the precision or accuracy of these tests are. And you should never use a test that's not actionable, that doesn't inform clinical care. Getting a number on biological age is not actionable. So to me, it's irresponsible for medical providers to be recommending and using these tests for those reasons. And I know there are people who disagree with me, but I've never heard anybody disagree with me and actually give a rebuttal to those three things that I just said, right? So it's frustrating. And I would like to see longevity doctors who are using these tests be more thoughtful and rigorous and responsible in the way they are caring for their patients.
Our guest today is Dr. Matt Kaeberlein. He is one of the world's most respected aging scientists. He trained in Leonard Guarenti's lab at MIT and became widely known for his work on rapamycin and co-founding the Dog Aging Project. He also co-founded Ora Biomedical, a longevity drug discovery company, which runs the WormBot screening platform, and Optispan, a healthcare technology company with several clinical programs, and a podcast about evidence-based longevity. He's also an affiliate professor at the University of Washington, fellow of the American Association for the Advancement of Science, the American Aging Association, and the Gerontological Society of America. Dr. Kaeberlein has published more than 250 scientific papers in the field of aging biology and has received several prestigious awards. And above all, Matt has a reputation for being honest about both the promise and the limitations in this field. Matt, welcome to Levity.
Thanks, guys. It's a pleasure to be here.
You started your career in the mythological Guarenti lab. It was like a hub for early aging research, right? And you were there at the same time as both David Sinclair and Brian Kennedy. I thought I was going to show you now an image from that time. Do you know what image I'm talking about?
I'm not sure.
Okay, let's see. Let's see if I can bring it up here.
Is it from Lenny's book?
Could be. I saw it on I think it was Brian Kennedy who maybe retweeted it on X.
Okay.
So we'll see if I can bring it up here.
Oh yeah, there we are. I think that is from Lenny's book. Yeah.
Okay, I haven't read it. What do you think when you see this image?
The good times. I feel very fortunate to have ended up in the Guarenti lab at the time that I did. It's great to see all those familiar faces, many of whom I haven't seen for several years. So, when I went to graduate school, I thought I was going to do structural biology or X-ray crystallography or something like that. And I heard a talk by Lenny right after the first semester in graduate school where he spoke about how his lab, just at that point within the last 5 or 6 years, had started studying the biology of aging. This was in yeast, of course. And he talked about the molecular mechanism of aging that was actually the work of David Sinclair and others in the lab, where they identified the ribosomal DNA as a key locus of aging in yeast cells. And, I don't know even to this day exactly what it was about that concept that really resonated with me, but I immediately became fascinated with the idea that we could use genetics and molecular biology and biochemistry to study something as complicated as the biology of aging. So I went and talked to Lenny, ended up joining his lab for my PhD thesis, and have stayed in the field since then. So again, it was a really fun time to be in the Grenti lab, and it was a really fun time to be in the field at that point. It was, this was probably 7 or 8 years after Cynthia Kenyon published her paper on the DAF2 mutant. I think, by that point, at least for people within the small aging field, and it was pretty small at the time, we understood that aging was a biological process. It was genetically modifiable. It was environmentally modifiable, but almost nothing was known about the mechanisms that were underlying aging. And so there were huge opportunities to do, what I think of as discovery science, and really, in an unbiased way, let the biology tell you what is most important about the aging process. And it felt like, every week a new gene was being discovered and a big paper was being published. So again, I just look back at that time and I feel very fortunate to have gotten onto the path that I got on. And I owe Lenny a debt of gratitude for getting me on that path.
Mm. What happened after that period of time? What did you do, and how did you end up doing what you do now? I know your career is rich, but if you could give the brief tour.
Sure. I would say, it's certainly nobody's career is a linear path, but I would say that, more or less, I knew by the time I finished graduate school that I wanted to continue working on the biology of aging in some way, shape, or form for the rest of my career. I took a look right out of graduate school. So this would have been, 2001, December 2001, I think is when I finished my PhD thesis. I took a look at a couple of academic postdocs. This was in Boston, where I lived at the time. But ended up, one of the labs I looked at was George Church's lab at Harvard, and ended up through George meeting a former student of his named Pete Estep, who had started his own company in the longevity space. It was actually called Longenity. And so I spent quite a bit of time talking to Pete. I really bought into his vision. Unfortunately, we were about 2 decades before our time. We were creating biological aging clocks in humans before the technology was really there to do that. But it was really all about trying to identify, actionable biomarkers at the molecular level of human aging. So I spent about 1.5 years, 2 years doing that. And then when my wife finished her PhD thesis, she was at Northeastern at the same time I was at MIT, we decided to move back to the Pacific Northwest, family reasons, and we both, love the Pacific Northwest of the United States. And then I started an academic postdoc at the University of Washington. I was actually a postdoc with Stanley Fields, who is very well known for creating the yeast-2 hybrid assay. A lot of people think I did my postdoc with Brian, but Brian was already at the University of Washington, Brian Kennedy, at that time. And so we started collaborating extensively. And, that has really, to this day, continued to be one of the, in my view, certainly personally, great scientific collaborations, but also great friendships that I've had. And we published, more than 100 papers probably together, did, I think a lot of really valuable work related to the biology of aging, identifying dozens, maybe hundreds of genes that affect longevity. And I think one of the things that Brian and I can point to as contributions that we've made is really helping to solidify the idea that aging, but the biology of aging is to some extent conserved across the animal kingdom. It's funny when I look back, when I was in graduate school, that was not accepted, generally speaking, even within the field. I still find it amusing at that time. You had the people who did geriatrics, who studied old humans, saying you can't learn anything about human aging by studying mice. And of course, the people who studied aging in mice, they couldn't complain about the humans. So they were like, you can't learn anything about studying aging in worms and flies. And then the worm and fly people didn't have anybody to pile on to except the yeast people. So they were like, you can't learn anything about studying aging in yeast. And I think both Brian and I were sort of frustrated by not so much that that necessarily was untrue, we didn't know at the time, but the fact that people were very dogmatic in their views without actually having any data to support it. So as a postdoc, one of the things I set out to do was just answer that question. And so Brian and I did a comprehensive comparison of all of the genes that at that time we knew affected longevity in yeast and in worms, and asked, is there overlap? And it turns out there is statistically significant greater overlap for genetics of aging. So I think, and we certainly weren't the only people thinking this or doing this, but I feel proud of the fact that we've helped contribute to what now I think everybody who knows anything about the biology of aging would agree with, which is that at least some aspects of aging at the cellular, molecular, mechanistic level do seem to be shared across the animal kingdom, which is important because that gives us tools now to understand aging biology with the hope that those tools will be relevant for human aging. And then I became a professor at the University of Washington and ran my own lab for 15 years, and then left academia 2 or 3 years ago to focus on longevity in a little bit different way. But throughout it all, the underlying theme has been to try to understand, what are the most important factors that influence the biology of aging, with the recognition that if we can do something about those factors, that gives us an opportunity to have a very outsized, I would say, impact on health span and potentially lifespan in the real world, in people and also in companion animals.
Yeah, and one of the fields that you are that many relate to you when I think of you is, of course, the field of mTOR inhibitors and rapamycin. And I think of it. I think that David Sabatini made some foundational work there. How did you end up working with and becoming interested in rapamycin?
Yeah, sure. So again, I alluded to the fact that, when I first came into the field, it was ripe for what I call discovery science, or unbiased large scale approaches to understand biology. And so when I began my postdoc, I think Brian and I both, we had a series of conversations where, it became clear that we were both of the opinion that in some ways, the field had already started to narrow a little bit, and that people became very hyper focused, in my view, on things like sirtuins and insulin signaling, and that there were opportunities outside of that to understand what else is out there related to longevity or the biology of aging. So we set out to do an unbiased genetic screen for genes that influence lifespan. And again, we were working in yeast at this point. Other people in parallel were doing similar screens in C. elegans using the large-scale RNAi libraries. And we were very lucky that within the first 500 or so genes that we looked at in yeast, one of them was the yeast version of mTOR, which is called TOR1. And what we found was that the yeast deletion of TOR1 had this very large increase in lifespan. And I would love to say that, we were really smart and we knew TOR was going to be important, and so we went and looked at it, but we weren't. We were lucky, but we were lucky in a smart way because we did the right experiment, which was the unbiased genetic screen that pointed us to TOR. That's how I became interested in TOR. At that time, I didn't know much about TOR biology or mTOR biology, but I knew enough to go to the internet, which was, still pretty in its early days, but PubMed existed back then, and ask, what do we know about TOR? And of course, then I found the work by David Sabatini and many others that had fleshed out the biology of TOR. But at that point, nobody had connected it to aging yet. And so immediately that was interesting because mTOR is, of course, a nutrient sensor. It's one of the key sort of nutrient sensors that all cells have, at least all eukaryotic cells. And so that in our minds suggested the hypothesis that the TOR1 mutant might be mimicking some of the effects of caloric restriction, which was well established in the field as a longevity intervention. And so we did a series of experiments to kind of test that hypothesis. We obtained data that was consistent with that hypothesis. And so we published our paper, I think in 2004 or 2005 in Science. And it was one of these interesting things that happens in biology sometimes where 4 different labs all independently in 3 different organisms hit on this pathway within a year of each other and published papers reporting that various ways of turning down mTOR signaling could increase lifespan in yeast, in nematode worms, in C. elegans, and in fruit flies. And so I think the combination of all of that work, sort of set the stage for the idea that this is probably an important conserved regulator of longevity that is related to nutrient signaling, potentially caloric restriction. And then, of course, a few years later, the interventions testing program showed that rapamycin, the drug that inhibits TOR, could increase lifespan in mice. So you asked specifically about rapamycin. When I did this initial literature search on TOR, of course, I found out that there was a drug called rapamycin or sirolimus in clinical use. It's the same molecule. That is an inhibitor of TOR. And then, in fact, rapamycin, the drug, was critical in the research world to the work that David Sabatini and others did, fleshing out the biochemistry of mTOR, because what they could do was find mutants that were resistant or sensitive to rapamycin. So I realized there was this drug that was an inhibitor of mTOR. In our hands, the genetic mutant knockdown of mTOR was long-lived. It was an obvious experiment to test whether the drug would mimic the effect of the genetic mutant and increase lifespan. It did. We published that paper in 2006. That was the first paper that showed that rapamycin, the drug, could increase lifespan. Again, that was in yeast. And then I mentioned 3 years later, the interventions testing program found that the drug could also increase lifespan in mice.
In elderly mice as well.
That's right. Yeah. And I mean, that's an interesting story because that was not the way that experiment was designed originally. It was sort of a happy accident that it took them about a year to figure out how to get the rapamycin encapsulated so that it could get through the stomach into the small intestine for release. Just because of the way the infrastructure of the interventions testing program operates, they had to start the other experiments because they test 5 or 6 or 7 drugs at the same time every year. And so I don't think anybody at the time expected the experiment to work, to start giving it to mice when they're 20 months old, which is roughly the equivalent of a 60-year-old mouse. But the experiment had already started, so they were like, well, we might as well go ahead and do it. And it worked, right? And that, again, I think, in my view, that's one of the most important results in the field since I've been in the field. The observation that starting treatment with rapamycin at 20 months of age robustly increased lifespan in mice. And we now know you get more or less the same magnitude of benefit from rapamycin starting late in life as you do early in life. But at that time, the paradigm was that you really had to start interventions early in life to get a large effect. And the rapamycin result was the first time that was really disproven. And I think now we know there are lots of interventions that you can start later in life in mice. Maybe lots is maybe that's an overstatement, but more than one, at least a handful of interventions you can start late in life and still get very robust effects on lifespan and various health span metrics.
Which are those interventions that we know of, by the way?
Well, so acarbose was the second one from the interventions testing program. Canagliflozin has now been shown. I think 17-alpha estradiol has now been shown. And I think as people have gone back and really taken a closer look at caloric restriction, when I was a graduate student, the dogma, more or less, although there were a few people who disagreed with this, was that you really had to start caloric restriction early in life in mice to get the full benefit. I think that's probably still true. You do have to start it early in life to get the full benefit, but you can get benefits from caloric restriction in mice starting later in life for at least a variety of health span metrics and probably lifespan as well. So there are a few other things that have been reported to increase lifespan when started late in life, but they haven't necessarily been reproducible. So those would include things like nicotinamide riboside or alpha-ketoglutarate. That doesn't mean that they aren't real. It just means that for whatever reason, the initial attempts to reproduce the lifespan extension didn't hold up.
When you talk about a robust effect, what are we talking about here? How much time?
Yeah. Well, right. So with rapamycin, about the best that's been achieved is 25% median lifespan extension. It's important, though, when you start talking about percent effects, which of course is what we're going to do, because that's the easy way to understand it, that can be very misleading when we're talking about lifespan experiments, especially in laboratory rodents, because the percent increase is, of course, dependent on how long the control animals lived. If they were short-lived, then the denominator in that equation becomes small, and the percent effect gets artificially amplified. The 25% effect with rapamycin is with long-lived controls. So when you look at the absolute numbers, the best that I'm aware of is about, for median lifespan from just a three-month treatment with rapamycin in middle-aged mice, about I think it's about 1,050 days median lifespan and a maximum lifespan of about 1,400 days, which is very good historically compared to other longevity interventions. So it's a very robust effect when you stack it against other longevity interventions in mice.
So we just need to translate this to 25% for humans, and we get a quarter of a century more time.
Yeah, I mean, again,
this is what we're after. I mean, it's nice for the mice, right? But sorry.
Yeah, no, I agree with you completely. I think that's one of the questions is how well will these things translate to humans, and assuming that they do from the biological perspective, what will that mean for median or maximum lifespan? Unknown. I mean, we can all speculate on it, and I think there's value in speculating, but at this point, we really don't know.
We could spend a lot of time talking about the backstory of rapamycin, but I think we're just going to skip it because it has been talked about at so many other places.
I've talked about it a lot, that's for sure.
Yeah, and so we can link in the show notes to more information about that. It's a fantastic backstory, so it's well worth reading up on if you haven't done it. But Patrick was talking about how do we translate this to humans, and I guess one of the ways we could actually inch closer to that is through the dog aging project. Can you tell us what that is and what the status is of that project now?
Sure. Yeah. So the dog aging project is primarily a large scale, what we call longitudinal study of aging, meaning it's mostly observational. I'll talk a little bit about the clinical trial component, but the largest part of the dog aging project is observational. And the longitudinal piece means we're following dogs over time. These are all companion dogs, pet dogs living with their owners in the real world, no dogs in the laboratory. And there are really, I would say, two overarching goals to the dog aging project. One is to understand the biology of aging in pet dogs. What are the most important genetic and environmental factors that influence health outcomes, longevity in dogs? The other goal is to do something about it, right? To use the information that we get to have a positive impact on health span and lifespan in dogs. A third indirect goal, of course, is to inform about human aging. And so, one of the questions would be, why would dogs be a better model for human aging than laboratory mice? I think there are a variety of reasons why you can make that argument. The most obvious is that companion dogs share the human environment. The vast majority of aspects of the human environment that are going to be relevant for health span and lifespan are shared by our pets. Diet is really the only place that I can point to where, for most companion dogs, their diet is substantially different from the human diet in terms of composition, but the impact of diet on health span and lifespan, again, is likely very much conserved. So that environmental diversity is something in the laboratory that we actually do everything we can to limit, right? We want to only study one variable at a time. Yet we know that human longevity is somewhere between 50 to 80% environmentally determined. So environment's important, and we can actually start to understand that in companion dogs. I think the genetic piece is also very interesting and powerful there, given that most studies in the laboratory are done in genetically inbred mice, not all now, but most, whereas dogs have this very complex and unique genetic architecture combined of purebred and mixed breed animals. So that adds another dimension. And then, of course, dogs age about 7 to 10 times faster than people do biologically, which means we can do these experiments in a time frame that's much more amenable to scientific discovery and, of course, to funding agency, funding timelines, which from a pragmatic perspective is really important. So those I think are the primary factors why dogs are probably a very powerful bridge from the laboratory to human aging. And then I think there's also the intrinsic value that I alluded to earlier of being able to increase lifespan and health span in people's companion animals. The statistics tell us that well over 50% of dog or cat owners consider their companion animals to be part of their family. And if we're able to increase lifespan and health span of people's family members, that's enormous, right? So I think it is important not to underestimate the intrinsic value of being able to do that for companion animals as well.
Is there any like physiological reason to think that dogs would be closer than model animals than rats or mice or other?
Yeah, I mean, body size in larger dogs would be the one thing you might point to. Of course, dogs are interesting because within the species, right, there's such a range of body sizes. Genetically, not really. The distance between dogs and humans and mice and humans is roughly comparable. And of course, there are going to be primate-specific features of aging that neither dogs nor mice are going to recapitulate. So I'm not really one to argue strongly that we can say that the physiology of dogs is that much closer to humans. I think the other aspects that I've already alluded to are plenty of justification for why it makes sense to do this in dogs. The one thing I will say that dogs provide, which again mice don't, because of their larger body size and because we have a relatively sophisticated healthcare system for companion animals in the form of veterinary medicine, is we are able to monitor many more subtle features of aging in companion dogs than we are typically able to do in laboratory mice. So functional changes, body composition changes. Veterinarians already have a lot of experience in what does an old dog look like and what are the changes. And so I think we have the opportunity to do a more comprehensive assessment of health span metrics in companion dogs than is typically done in laboratory rodents for those reasons. In that vein, though, it is also, worth noting, and this is sort of ironic, that on the molecular side, sometimes it's harder to do the experiments in dogs than that we would want to do, because many of the biochemical reagents, antibodies and things like that, haven't been developed in dogs. They've been developed in mice for research purposes, and they've been developed in humans for clinical purposes. They haven't yet been developed in dogs or cats. So we have to create those reagents in order to be able to do some of the experiments that we'd want to do, like antibodies to quantitatively assess mTOR signaling as just an example.
And talking about that, because I don't know, that sounds expensive. It might not be. You can say. But there was, I don't know, 1 year ago, 2 years ago, something like that, that funding was scrapped, right, for this project. What happened after that? What was that and what happened then? Sure.
Yeah. So maybe it's useful to give a little bit of history to sort of set the stage. And I mentioned there's a clinical trial component to the dog aging project as well. So that clinical trial is a clinical trial of rapamycin. It's a randomized, double-blind, placebo-controlled veterinary clinical trial with the goal really to determine, does rapamycin increase lifespan and improve health span metrics in dogs? So the dog aging project really got its start as an effort to create that clinical trial. This was 2013, 2014 or so. Daniel Promislow and Kate Creevy, who were the other directors of the dog aging project along with myself, had been thinking about a longitudinal study of aging in dogs at that point. And Daniel and I were co-directing the Biology of Aging course in Woods Hole, Massachusetts. That was a course that the Ellison Medical Foundation put on every year. So we spent 3 weeks, a couple summers in a row, with 20 students, and Daniel and I and a few TAs really immersed in aging biology. And so Daniel and I talked a lot about, his thoughts around dogs as a longitudinal model of aging. I'm a dog person. I've always had dogs. And I had this light bulb moment at some point during that course where I was like, of course I understood why studying aging in dogs had value and the reasons we just talked about. But for me, I had this, crystallization that we already know about things like rapamycin in mice that slow aging, increase lifespan, seem to improve health span. Some of those things are going to work in dogs. And we could do a clinical trial in a few years. I hadn't done the math to figure out exactly what that would look like at that point, but I realized we could do a clinical trial in a few years in dogs to prove whether or not an intervention slowed aging. And as soon as I had that realization, of course, I thought about my own dogs and I wanted them to live longer and other people's dogs. And I had to do it. Like it became something that I was going to do. And, I have a lot of personality flaws, and I don't know if this is a flaw or a strength, but when there's something important that I see needs to get done, I go do it, or I do everything I can to get it done. And so I immediately started trying to figure out, how do I pay for a clinical trial to test this? Raised some money, and was fortunate to get some very early media attention, again, sort of accidentally. I was being interviewed by a reporter for Nature magazine about a completely different story. And at that point, I had created a conference in Seattle, like a very small couple-day conference to get key stakeholders together to talk about how you would study aging in dogs. But of course, in the back of my mind, it was like, can I get some of these people to give me money to do this clinical trial? So I told her about this conference and that I wanted to do this clinical trial of rapamycin in dogs. And she got so excited about that, she wrote a story in Nature about that instead of what she was going to do the story on. That got picked up by the UK Guardian. That got picked up by our local paper, the Seattle Times. And the reporter came out and interviewed Daniel and me at the University of Washington. And we knew the story was going to run on Monday. And, I'm sitting at home looking at my wife who was helping. She did a lot of the early work on the project at this point, about how we were going to do this pilot clinical trial at this clinic in Seattle. And I'm looking at her and I'm like, when that story runs, we're going to have a bunch of people who want to sign their dogs up for this study. What should we do about that? She's like, we should probably put a website up. And I'm like, that's a good idea. What do we call this thing? And where's it's aging and dogs. We're going to call it the Dog Aging Project. So literally she built a website over the weekend so that owners could nominate their dogs to participate in this pilot clinical trial. That's how the Dog Aging Project was born. This was 2014, 2015. And it took about 3 years from there to actually get the first NIH grant to support the project. So I was successful at raising another few $100,000 to do a second pilot clinical trial after the first one was actually shockingly successful, both in terms of showing safety and giving a hint of efficacy from a small pilot clinical trial. But it took 3.5 years to get the first real NIH money, which was extremely frustrating, still is extremely frustrating to me, how slow and difficult it is to get any important big ideas funded in academic science. It's just really, really hard. But we did. And so that grant supported the longitudinal study. That grant was really to build the longitudinal study of aging. We proposed to enroll 10,000 dogs at that time into the longitudinal study of aging, do genetics and multiomics and collect survey data and veterinary records. And to support the clinical trial. And that clinical trial, that was going to be like the phase 3 version of the rapamycin clinical trial.
Right.
We'd done 2 safety trials by that point. That was going to be the pivotal. Efficacy. Does it work? 580. At that time, it was 270 dogs, I think, were going to be enrolled in the clinical trial. That would give us statistical power to detect, I want to say, a 15% increase in lifespan, we believed, in the cohort. So that was funded mid 2018. The money didn't arrive till the end of 2018. That's just the way things happen at NIH often. So we started building this thing. We started planning the clinical trial, putting the protocols in place, getting all the approvals, building the infrastructure for the longitudinal study of aging. And then we all know what happened in 2020, right? We had this global pandemic. All the veterinary clinics were closed. And so Daniel, Katie, and I and the rest of the team sort of looked at each other and we're like, oh, well, crap, what do we do now? We can't enroll any dogs in the clinical trial. So we decided to focus on increasing the size of the longitudinal study and on recruitment into the longitudinal study. That grew the study to 50,000 plus dogs, which is where it's at today. And then over the rest of that grant, so these NIH grants are 5-year grants, we were successful in getting the clinical trial about 25% enrolled. So it was hard, right? Coming out of the pandemic and then having to get all of the veterinary clinics, into the program and trained. And so we submitted a renewal in 2023. Again, funded in 2018, renewal goes in 2023. And the review panel chose not to refund the project. I mean, I could talk about all the bullshit reasons, but that's just the reality of the situation, right? They chose not to refund the project, despite the fact that it, grew to 5 times the size that we targeted, and is arguably the most impactful study in the field of geroscience to date. They chose not to refund it. The leadership at NIH chose to go along with the review panel recommendation. And so we had to really try to do everything we could to keep the lights on. We obviously stopped enrolling dogs into the clinical trial actively, maintained the dogs that were in there. Again, I went out and sought philanthropic funding. We were successful. Again, I'm extremely grateful to the donors who stepped up in raising, $1 million+ to maintain the infrastructure and the project. The clinical trial has since been refunded, so new grant went in. That did get funded through the normal NIH funding mechanism, the CMAD study section. So kudos to the folks on CMAD. The longitudinal study has not yet been refunded. The grant is going in right now. The team is optimistic, hopeful that the value will be recognized and that the project will be supported going forward. So the clinical trial will be completed, assuming that the allocated funding is actually dispersed the way we anticipate that it will be. Historically, that's always been the case, but right now there's very little that's certain when it comes to federal funding in the United States. But hopefully it will be dispersed, and that clinical trial will get done. And of course, I'm cautiously optimistic that the longitudinal study will be funded and that we will be able to continue that work. I will say, though, already there's been huge value because we've created this enormous data set from the longitudinal study to date that is freely available to the academic and nonprofit community at the Broad Institute. Anybody can go get access to that data and do studies based on the data that's been collected to date. So I'm confident that the impact is there. I hope that it is recognized and will be supported so that we can continue to have a much larger impact going forward.
I mean, is there anything specific that you can say that we learned from the data so far?
Yeah. Well, so with respect to rapamycin, for sure, we've learned that this can be administered safely in companion dogs. There is evidence for improvements in heart function, activity, quality of life, but those come from the smaller pilot clinical trials. The large study is still blinded, so I can't tell you in terms of efficacy anything about rapamycin from that study. And then from the longitudinal study, yeah, there have been, again, I don't know what the current count is, 70, 80 plus peer-reviewed papers published from the longitudinal study so far. Some of the interesting, and again, people need to recognize, due to the nature of the study, it's observational. These are going to be correlative results, right? Just like it is from human epidemiology. Some of the correlations that are interesting that have come out of it include things around meal frequency. So as an example, I didn't think this was going to work, but as an example, dogs that are fed once a day are at a significantly lower risk of developing 7 different age-related diseases. And in the other 3 conditions that we looked at, it was directionally going in that direction. It just didn't meet statistical significance. That's intriguing given all of the interest around caloric restriction and time-restricted eating and intermittent fasting. Of course, an alternative explanation there has to do with obesity, right? So it's a hypothesis-generating sort of result, as these things often are. Quite a few papers have been published on dementia in dogs. So many dogs, maybe I shouldn't say many, a subset of dogs will develop age-related dementia. And we can look at what factors are most associated with dementia risk in dogs. Age is the most, so that's good. That's what we expect. Age is the strongest predictor of dementia in dogs. But once you get outside of age, physical activity is the second strongest predictor. That, again, fits pretty well with what we think we know about dementia in humans. Sterilization status plays an important role in dementia. That's intriguing. That potentially has to do with sex hormones and their effect on the aging rate of the body and the brain. One thing, though, that's really interesting there is body size does not seem to impact the risk of dementia in dogs, not in the way we would expect, at least. So big dogs age faster than small dogs in pretty much every metric you look at. And of course, life expectancy is shorter in big dogs, except in the brain, or at least with respect to dementia. There is really no accelerated risk of dementia in large dogs compared to small dogs. that's really interesting, both from a biological hypothesis sort of perspective. The obvious hypothesis is this has to do with insulin signaling and IGF-1 signaling in the brain affecting cognitive function differently from the way it affects aging in the rest of the body. There's animal evidence to support that, laboratory animal evidence to support that. This also matches really well with what is seen in humans. Again, it's harder to see these effects because the body size difference in humans isn't as pronounced as it is in laboratory animals. But the data certainly support the idea that individuals of larger stature, now I'm not talking about body weight because that's confounded by obesity, but let's just say height. Individuals of larger stature seem to age more rapidly and live shorter than individuals of smaller stature in many ways, but not for risk of dementia in humans. So the biology seems to parallel pretty well from what has been seen in the longitudinal study in dogs to now in humans. And like I said, there's probably been 70 other studies that have been published, with a flavor like those that I've described, looking at different aspects of aging. And the one of the things that I think we can do in dogs that is hard, we can't really do in laboratory animals, is look at things like socioeconomic status of the owners, environmental pollutants. So there have been a couple of studies published looking at the air quality association with health outcomes in dogs, because we know that based on their zip code, water quality, exposure to various metals in the environment, things like that we can do in dogs that are you can do in humans, but the time frame is much more extended in humans before you see any age-related outcomes.
You have signed up so many dogs. Do you plan to do something else in terms of intervention than rapamycin? Are you trying to? Yeah.
Good question. I mean, certainly, I would like to. Of course, there's a resource allocation and infrastructure question that comes in there, right? So resource allocation, got to have money to do a clinical trial, and then infrastructure. Is the team in place? Is the infrastructure in place in terms of veterinary clinics to do another intervention? Of course, the infrastructure question can be answered if you have enough resources, right? So the answer is right now, no. I have no intention of doing another intervention clinical trial in dogs. I always recognized, but I'm not going to say never, because I think there are smart things to test that if the resources were there, it would make sense to test. But I will say, even when I was first building this thing, it was obvious to me that this was both an opportunity to test rapamycin, but also an opportunity to show people that it can be done and a way to do these kinds of clinical trials in the real world, to create a template, a map. And I'm gratified to see that has, in fact, had an impact. We now have for-profit companies that are pursuing these kinds of clinical studies in companion animals, both in the sort of supplement unregulated market, but also trying to go down the FDA approval path. Loyal is the most obvious example, where they are developing right now 2 different interventions that they are, in various stages of getting conditional approval from the FDA for lifespan in dogs. So I think, independent of whether the Dog Aging Project tests additional interventions, that it has played a role in creating both a playbook for how you do it and a recognition that there's value in trying to develop drugs to slow aging in companion animals.
I guess you could tell all those participants that it's not necessarily over when the dog is officially dead.
I'm not sure what you mean.
Our last episode was with Micah Mills, cryopets.
Yeah, I mean, again, so that gets into a very different realm than the way I usually think about longevity and health, right? So certainly for people who want to cryopreserve their pets or themselves, I think I'm all for, you should have the freedom to do that. Whether or not, that's going to ultimately be a productive thing, of course, nobody knows, but I see the rationale for, well, there's nothing to lose. I at this point am not particularly optimistic about cryopreservation in the current state of that field, but I'm not an expert. And like I said, I understand the rationale for I've got nothing to lose.
This episode of Levity is brought to you by Vitalism Foundation. It's a community of action driven by Vitalism, a new moral philosophy whose first tenet is that life and health are good, death is humanity's core problem, and aging its primary agent. They're one of the few groups that truly understand aging as the emergency that it is.
Vitalism's goal is nothing short of monumental: to allocate 1% of global GDP to this project. It's ambitious, but it's exactly what's needed to tackle aging head-on.
As a member of Vitalism, you'll get access to a private community, exclusive content, and invites to special conferences. Plus, you'll receive insider prices on longevity wellness services from Vitalism's mission-aligned partners.
But more than that, you will be supporting a mission that's too important to leave to others to tackle.
You should really join us. Follow the link in the description below. For a limited time, you get 30% off forever. Just use the promo code LEVITY at checkout.
Again, that's 30% off forever with the promo code LEVITY. Let's make a difference together.
I do think that I was also going to mention Kai Mills that we had on the podcast.
Mm-hmm. Yeah.
So he's running a company called CryoPets, a startup.
Yeah.
But rather than discussing how feasible cryopreservation is, I think it's interesting though that people are very much inclined. I mean, he has a waiting list for this. Whereas there's no waiting list for preserving humans.
Yeah.
So I asked him, I mean, you're going to, don't you tell the owners that so they're going to preserve their pets, but they will be dead when the pets reawaken, so to speak. Yeah. And it's interesting. It's a little bit, I feel, the same kind of phenomenon with the way I see the dog aging project or what Loyal is doing, that if people are not aligned in their views about human aging, they seem to be pretty aligned on their views on pet aging. They don't want their pet to die. So I think there's some cultural phenomenon there that's worth exploring more.
I would agree with that. I mean, again, obviously, there's a lot of complex human psychology that comes into play here, right? And culturally, the way that we think about aging and death has a role there for sure, and that's even different among different societies, right? So, one thing I would say though is I believe, and again, I could be wrong, but it is my belief that the people who are enthusiastic about the rapamycin clinical trial or Loyal or a drug or a supplement to slow aging in their dogs, that's a little bit different psychology than the people who are interested in cryopreservation of their pets, but not themselves. And we could explore that, but I think the larger question that you're posing is, first of all, observationally, there is a difference in the way people think about what they're willing to do for their own longevity versus what they're willing to do for their pets' health and longevity. And why is that? And should it be the case? One of the things, again, that was immediately apparent to me very early on with the dog aging project was the opportunity to reframe that discussion around human aging by helping people understand through the dog aging project that aging is a biological process, right? And that, because I think that's starting to become a little bit more widespread knowledge, but even still, once you get outside of the longevity bubble, the vast majority of people don't have any concept of the idea that aging is a biological process and that it is affected by genes and environment, right? So part of the rationale for the dog aging project was to have an impact among the broader public of just that concept, getting more attention and understanding. And I think as that happens, and I think we're starting to see this, as that happens among a broader constituency of the public, there's all sorts of really interesting ripple effects that come from people just understanding that there is a biology of aging, right? That we can do something about it. That will, I believe, have an impact on policy, on the way people think about the importance of maintaining their health earlier in life, and the way that people start to approach the idea of growing old and eventually dying. And again, it's really complicated because there is absolutely a set of people who become very focused on death, right, rather than health. And I'm not sure that's healthy. Again, I think that's a psychological question, and it's an interesting conversation to have. I personally don't think it's really healthy to spend all your time worrying about death. I think it's much more productive to spend your time thinking about how do I maintain function and health for as long as possible, and joy. We don't talk about joy a lot, but personally, I don't see a lot of point in being alive if you're miserable. But I do think this all kind of feeds into the conversation, and the Dog Aging Project, or Loyal, or just this idea that we can have an impact on the health and longevity of people's pets by targeting the biology of aging, is a valuable educational tool in expanding the message, right? That there is a biology of aging. We can do things about it, and we should, right? We should learn about the biology of aging, and we should do what we can to keep people and dogs functioning as well as we possibly can for as long as we possibly can.
I guess at this point, people also want to know and ask, when are you going to talk about humans? And because people are already using rapamycin, at least some do. Sure. And I know, Matt, that you've been using it for a very specific ailment that you had. Could you talk us through why you chose eventually to actually try rapamycin for yourself?
Sure. Yeah. So before I do that, I think it's worth saying, right, that a couple things are worth saying. One is, obviously we don't know that rapamycin slows aging in humans yet. We don't know if people taking rapamycin are going to live longer and be healthier. There are a whole bunch of anecdotal observations that I think point the arrow in the right direction, and I'm happy to talk about those. But we don't know the answer yet because we don't have. First of all, it hasn't been done for long enough in people to know the answer, and we don't have the randomized clinical trial data. That's true not just for rapamycin, that's true for every supplement, every medication people are claiming is a longevity intervention. But the only thing where I would say we can be, really pretty sure that it affects the biology of aging in humans, I would put diet, exercise, sleep quality probably, and human relationships in those buckets, right? Those are the things that actually we can have some high level of confidence have a positive impact on the biology of aging. So it's just important, I think, to set expectations, because I, as you know, try to be pretty precise and cautious in my language. Not everybody does, and there are a whole bunch of charlatans out there claiming things are longevity drugs or supplements that aren't. And I think it's just important for people to understand that. Okay, so having said that, if you'd asked me 10 years ago, should people be taking rapamycin for longevity, I probably would have said, it's probably not. There are some risks associated with the drug. It has side effects in organ transplant patients. We don't know enough yet. It's probably not worth the risk at that point. And then I think two things happened. We got more data. We got more data from people using rapamycin off-label. That just means for a reason different than the FDA-approved indication. At different doses than organ transplant patients take it. And I had a personal experience that changed my mind. So my personal experience was, this was 2020. So early, even before COVID, I started having a lot of pain in my right shoulder. And, I like to lift weights. I like to be pretty active. And so that's when I really noticed it was every time I would do lifts, especially chest or shoulder, I would have really, really extreme pain in my shoulder that would go away after a couple of sets. And that was weird because most injuries don't do that. But like most guys, I kind of hoped it would just go away on its own. I didn't do anything about it, didn't go see a doctor. And then it got to a point where I was really having trouble sleeping. My wife was getting pretty annoyed with me. And we have a park across the street from our house, and I went out to throw a football with my son, and I couldn't do this kind of throwing motion, right? And so I had to look at him, and I'm like, man, I'm sorry, Jace. I can't do it. It hurts too much. And so that was sort of like an existential crisis moment where, like, crap, I'm getting old. but also like I need to get this fixed. And so I had convinced myself I had a torn rotator cuff. And so I went to my primary care doc and I'm like, Doc, I got a torn rotator cuff in my shoulder. I want you to give me a referral to a specialist so I can get surgery and get it fixed. And he's like, most primary care docs, like, no, I want you to go to physical therapy, give that a shot. And I'm like, all right, I'll try physical therapy. So I did. That actually made it worse. So I spent probably 5 weeks doing the physical therapy a couple times a week. That made it worse. So I went back to my primary care doc and I'm like, okay, I tried it your way, didn't work. I want the referral now. And he fortunately gave me a referral to go see a orthopedic specialist. Within 10 minutes, the guy's putting my arm behind my back and where does it hurt? When does it hurt? Within 5 or 10 minutes, he's like, you don't have a torn rotator cuff, you have adhesive capsulitis. And I'm like, what's adhesive capsulitis? And he says, it's inflammation of the shoulder capsule. It's called frozen shoulder, and it's very common in adults of your age. And mostly in women, but men get it too. And, maybe it'll go away in a year. That's what the guy says to me. He's like, maybe it'll go away in a year. And I'm thinking, I cannot do this for another year. So that's when I understood what it was, that it's an age-related inflammatory condition. Of course, I'd been studying rapamycin. And by this point in my lab, in mice, we knew that rapamycin could increase lifespan. It was very, very potent at knocking down inflammatory markers, age-related inflammatory markers across every tissue and organ where we looked. And in fact, we had just published within a year or so at this point that especially, this is sort of irrelevant to the shoulder, but in my mind, it was, again, more evidence that this might work, that in the oral cavity, where there's a lot of inflammation with age, rapamycin just basically floored it back to the youthful levels. So I thought, okay, I'm studying this drug in the lab. It's really good at knocking down age-related inflammation. I've got a very specific age-related inflammatory condition with a phenotype that I'm going to know, whether it's helping or not. So I'm just going to give it a try. And so again, I'm lucky in the sense that I have access to medical professionals who will, help me on these types of journeys, which not everybody does. At this point, it wasn't trivial to get a doctor to prescribe rapamycin for this kind of a self-experiment. So I just basically, came up with my own experiment for what I was going to do. I was going to take 6 milligrams of rapamycin once a week for 10 weeks and evaluate at the end of that period, whether I wanted to keep taking it or not. And within a couple of weeks, I had notable decline in the pain, for sure. My sleep got better. And by the end of the 10 weeks, it was pretty much gone. I'd say 95% range of motion back. I could go throw a ball with my kid if I wanted to. I was sleeping well. It didn't hurt anymore. So could it be placebo effect? Sure. This was so pronounced that it's hard for me to believe that it was all placebo effect. I can't disprove it, but it's hard for me to believe that. And I know myself personally, I'm just not one of those people who's prone to placebo effect. If anything, I go the other direction because I'm hyper skeptical when I've done these other kinds of self experiments. So I don't think it was. So since then, I've taken rapamycin off and on, usually for 3 months at a time. And usually I take a 3 to 6 month break in between 3-month cycles, not because the frozen shoulder ever came back, but just, because I feel like the risk reward favors reward at this point. And the hypothesis is that you knock down the age-related inflammation. It takes a while for it to come back. You knock it down again. Might taking it all the time be better than taking it intermittently? Yep. Might not taking it all be better than taking it intermittently? Yep. But that's what I'm doing. So, and I don't walk around saying everybody should take rapamycin. I do think now that I have collected data from a lot of people and from talking to lots of people, there are specific use cases where people like me can have fairly profound positive effects on chronic inflammatory conditions. And so that's where I see the most likelihood of rapamycin being useful off-label today. And those include obviously frozen shoulder, but a lot of chronic conditions that are the result most likely of inflammation, and particularly in the area of persistent viral driven inflammation. So we're all familiar with long COVID. We did a study of people using rapamycin off-label, and that study gave some evidence that rapamycin could be beneficial both for reducing the likelihood of moderate to severe COVID-19 infections. This was all data taken in the height of the pandemic, and also in the likelihood of people experiencing symptoms that would be consistent with long COVID. Now there is a lot of data accumulating. In fact, there was this really cool paper published within the last 3 months or so looking at chronic fatigue syndrome. So a collection of physicians and psychiatrists who had been using rapamycin off-label in patients with chronic fatigue syndrome. What they found was about 75% of the patients who were given rapamycin had pronounced improvements in their chronic fatigue symptoms. And the majority of those people who showed improvements were people whose chronic fatigue syndrome was post-viral infection. So this leads to a hypothesis. It's speculation, but it's a pretty plausible hypothesis that chronic inflammation driven by persistent viruses or antigens that persist from viral infections is driving chronic fatigue, chronic pain in some people, and rapamycin is particularly effective at blunting that. Is that slowing aging? Not necessarily, but is it useful? Absolutely. For those people, it's really useful. So I'm enthusiastic about that. The other place that I'm particularly enthusiastic about rapamycin is, at least in a subset of people who are at high risk for dementia and Alzheimer's disease. Again, there have been a few studies recently in people who are heterozygous for ApoE4. That's the greatest genetic risk factor for Alzheimer's disease. In those people, you can actually see, of course, early cognitive decline sometimes, but early changes in brain volume and cerebral blood flow. And two different studies, both very small, but both showing the same effects. In ApoE3/4 heterozygotes, short-term treatment with rapamycin, we're talking 6 to 8 weeks, improved brain volume in a couple of specific brain regions, the hippocampus and the caudate nucleus, and also improved cerebral blood flow. And there's a whole bunch of preclinical literature in laboratory animals on rapamycin protecting against brain aging, cognitive decline during normal aging, and in a bunch of different mouse models of Alzheimer's disease. So again, reason to be optimistic that for that use case, there are opportunities. Would I love to see the randomized clinical trials? Absolutely. Is it frustrating that those haven't happened yet? Absolutely. I think, we are in a situation, in my view, where for certain people, given that we're not going to have that data anytime soon, the risk reward favors reward. So that's kind of where I stand on rapamycin these days.
How big is the world of people who deal with rapamycin? That is someone right now trying to look at whether they can develop, expand the label to include frozen shoulder, right, etc.?
Good question. Yeah. So to the best of my knowledge, nobody right now is looking at a label expansion in humans for rapamycin. There are plenty of ways you could expand the label to different indications. I don't believe anybody is doing those clinical trials. On the positive side, there are companies that are developing novel derivatives of rapamycin or other drugs that inhibit mTOR biochemically in different ways, and looking at those for new label indications. So new FDA approval, those are new drugs. Of course, those are long processes and very expensive process to go through. So this is where I think, unfortunately, the incentive structure right now for drug approval makes it difficult for drugs like rapamycin that have a lot of potential. There are other drugs in the longevity space as well that you could point to that have a lot of potential. It makes it difficult for those to go through the rigorous clinical trial processes we would want to see them go through in order to get the answers that we all want. I think, unfortunately, where we're at today, there are some clinical trials happening for rapamycin, some senolytics, metformin, things like that. Those are all pretty small, and they're generally branded as safety trials, even though we already know rapamycin's safe. Like, it's kind of ridiculous to have more safety trials on rapamycin, but that's the way that investigators in academia can get small grants to do these kinds of clinical trials. The frustrating part is they never actually answer the question of efficacy. So we get a lot of these reports that hint at efficacy, but they aren't very good statistically, and we don't know is the real answer at the end of the day. So it's an unfortunate situation right now. In my personal view, NIH can and should do better. This is where NIH could actually play a leadership role. NIH has the resources and the infrastructure to do clinical trials. they could play a leadership role and say there is a need to bridge between academia and for-profit because these clinical trials make sense and they're not happening. So far, NIH leadership has not stepped into those leadership roles to get those clinical trials done.
But it seems a bit surprising, though. I mean, because as you say, it has been established that this is safe enough, and
yeah,
so it would seem that it wouldn't be so hard to try this on patients with, for example, frozen shoulders and see.
It's not hard. There is a bureaucracy you have to navigate. It's more a matter of resources. So, doing the large clinical trials to the standards that would be necessary for FDA indication expansion costs a lot of money. And pharmaceutical companies aren't going to invest in that for rapamycin because they don't have patent life on rapamycin, right? So the incentive isn't there for them to do those kinds of clinical trials, which is what I was alluding to, where I think that's a perfect example of where NIH could take the lead and do those sorts of clinical trials because it's in the best interest of the American public and human health, which is what they're supposed to serve.
It's so interesting. I can't really quite understand it, why the NIH seems like they're actively sabotaging the field. I mean, they know by now that there is merit to the neuroscience hypothesis, right? They've certainly read Andrew Scott's paper on how much money we could save by just extending life by 1 year for Americans.
I'm not sure they do, honestly. I think you're no. I mean, and this is not meant as anything other than just a reality check, right? I think when you get to the highest levels of policy in the United States, in any field, they are often not as informed about some of the important topics as they could and potentially should be in order to make those kinds of decisions. There's also a lot of bureaucratic red tape. The federal government in the United States is an enormous, enterprise. Shifting direction, even within a portion of the government like NIH, takes a long time. But the people who run NIH honestly don't have a lot of expertise or background in the science of aging. And to be fair, the field has sabotaged itself quite a bit by the bad actions of supposed leaders in the field that tarnish the reputation. Like, I think if you talk to high-level policymakers or government officials, many of them will have a negative taste in their mouth about the quality of science in the geroscience field because of the actions of irresponsible scientists. That's a fact. And so that has definitely played a role in slowing, I think, the ability of the science in the field to get the resource allocation that it deserves. There are things going in the right direction. To be positive, I'm involved with a group called the Alliance for Longevity Initiatives. I'm on their board of directors. I want to give Dylan Livingston a huge shout out. He's the executive director. He's done a phenomenal job with A4LI at getting traction within the federal government in the United States. There's a longevity science caucus in the U.S. House of Representatives that Dylan helped to get off the ground. It's got bipartisan support. I was actually at the annual meeting of A4LI earlier this year for a congressional briefing. I spoke there. Eric Verdin spoke there. And Dr. Oz, who's now high up in HHS or HMS in the U.S. government, gave sort of the opening introduction to that conference. And he used our language. He talked about the hallmarks of aging. He talked about senescent cells. He talked about the economic impact of slowing aging. That's the first time I have ever heard anybody at a high level in the federal government using our language. Like, he got it, or at least he'd been briefed enough where he sounded like he got it. That's progress. It can still be derailed by irresponsible actions. And so we need to guard against too much hyperbole, bad science, and be rigorous in our approach and show the scientific community that we're serious people trying to do serious science. I think, honestly, that is one of the most important things we can do right now if we want to shift the resource allocation more towards geroscience.
This got me thinking about, when you mentioned A4LI, got me thinking about the right to try law in Montana.
Yeah.
How do you feel about that?
Yeah, I mean, so I'm a supporter of that. I actually helped testify among the at the Montana congressional meeting when they were considering the first round of the expanded right to try in Montana, and I helped Representative Bogner draft some of that language. So I've been involved in that. I'm supportive conceptually of the idea that we need better legislative tools to allow people who want access to experimental therapies to get access to experimental therapies for their own health, whether that's a immediate, acute, life-threatening condition or not. I think part of this is about, and of course, I'm also of the mind that there needs to be appropriate regulatory structure put in place so that these things aren't abused and we don't have terrible, outcomes for people who are trying experimental therapies. It needs to be done responsibly. I think it's more likely to be done responsibly under the context of something like an expanded right to try law. I would love to see this done at the federal level in the United States. I actually believe that one of the real challenges in the clinical expansion of, I'm going to use the words longevity medicine, is the fact that so much of longevity medicine, it's not a huge proportion overall, but it gets a lot of attention. So much of the attention in longevity medicine gets put towards offshore clinics, gene therapy, experimental stem cell therapies that are being done outside of any regulatory environment. And my concerns there are, obviously, I'm concerned with some of the bad actors in that space who may not so much that the therapies are dangerous, they can be, but they don't have to be, but that they aren't always being performed in a safe manner. That concerns me because I think there are going to be bad outcomes that could derail a lot of the momentum that we've got right now. But I'm also concerned that we just don't get any useful data from that, right? There are all these people doing these things. Like stem cells are a great example. If you ask the vast majority of clinicians or scientists today, are stem cell therapies, and obviously that's a catch-all for a bunch of different specific ways you can use stem cells. But if you ask people generally, are stem cell therapies useful for longevity? Most people, including me, are gonna be like, who the fuck knows? Because we haven't got any data, right? And the reason we don't have any data is because all of this stuff is being done outside of any regulated infrastructure where we can actually collect that data and evaluate efficacy and safety, right? So, and again, I would put some of that on the FDA because they have chosen to not regulate these things instead of saying we're going to regulate it in a way that ensures we can actually get useful data and have some level of safety. And in the case of like stem cells, this is a good example. The safety there both is the procedure itself. So you go to the clinic, is it being done? What is the procedure? Is it being done appropriately? But also the manufacturing of these things, right? There's really no or little regulation around the manufacturing of these stem cell therapies or exosomes or peptides, right? And so a lot of the safety concerns come in from bad manufacturing practices that then can lead to allergic reactions and things like that in people, which again can give the therapy itself a bad name. Maybe the therapy's great, but there was a manufacturing problem which caused somebody to have a terrible allergic reaction that they died from or almost died from. So it's created a situation that I think is counterproductive on many levels, and it doesn't have to be that way. So all of this is to say, I think things like the expanded right to try in Montana give an opportunity to create a regulatory infrastructure and framework to start to collect some of the data that we need in order to evaluate these experimental therapies. Is that necessarily going to happen? We don't know yet because the regulatory framework and infrastructure hasn't been created yet in Montana or in other places that are thinking about these kinds of approaches.
Let's talk about Ora Biomedical now. You co-founded that company, and you're building something called the WormBot platform. You use the WormBot platform already. So right. What is that?
Sure. Yeah. So this story started again probably 10 years ago, maybe not quite that long ago. But so I mentioned earlier on in our conversation that I came into the field at a time where a lot of groups were doing large discovery science and unbiased approaches to understand the biology of aging. over time, and this is natural in any field as the science matures, the geroscience field narrowed. And in my view, it narrowed prematurely. And I think, and I'm not one of these people who bashes the hallmarks of aging. I think the hallmarks of aging are useful in many ways. But I think one anticipated consequence of the hallmarks of aging becoming as dominant a paradigm as it is that narrowed the thinking in the field dramatically. Before the hallmarks, people were doing a much greater diversity of research, or maybe I should say diversity of research in the field was supported much more broadly than it is today, because the hallmarks created a situation where it became very difficult, if not impossible, to get a grant from a federal funding agency to study anything that didn't fit within the hallmarks paradigm. And so I recognized this, like I said, 8 to 10 years ago, and it was concerning to me. And so I started trying to think about, how can we look outside the hallmarks? How can we do more of the sort of unbiased longevity studies that I grew up on in the field, for lack of a better way of saying it? And especially in the context of small molecules or other types of interventions. So people have done the genetic screens, although it is important to point out, I think there's a misperception among scientists in the field that we've already done the genetics of longevity. That couldn't be farther from the truth.
Yeah.
We have looked at loss of function genetics, so knock down or knock out genes in worms and yeast. Period, full stop. We have done nothing with dose response. We have done nothing with I shouldn't say nothing, but essentially nothing compared to the scale and scope of work that's been done for loss of function with overexpression. Alatin Kaya, who's a brilliant guy, I love Alatin, did an experiment where he looked, this is in yeast, so take it for what it's worth, but I think directionally this is very informative. He looked at, I want to say 40 genes, essential genes. Oh, that's the other place nobody's looked, is essential genes, because if you knock them out, you get a dead animal, right? He looked at 40 essential genes and he asked, what's the effect of overexpressing them one by one on lifespan? And the striking result was that well over 50% of them increased lifespan. It's a small number, but statistically, it's one of these things where you look at it and you're like, that's real. There's something fundamental about the biology of aging we don't understand. In fact, there's a lot of fundamental stuff about the biology of aging we don't understand because people stopped looking for it, in my view. So this was all recognizing that, and then thinking, how do we create tools to potentially allow massively large longevity intervention screening. So that was the concept. And how do we do it in a way that's affordable, recognizing that, nobody's going to throw $1 billion at this problem. It would be great if they did, though. We could make a lot of progress. So then the question was, where are you going to start? You're going to try to do this in mice? That would be great. That would be great because it's a mammal. But I wanted to test, at that time, I was thinking 100,000. I'm now at a million is where I think we should start. We should go up from 1 million interventions. But I was thinking, even 100,000, how are you going to do 100,000 lifespan experiments in mice? That's just not going to fly. So where are you going to do this? I thought C. elegans made the most sense because I was pretty convinced at the time we could create a platform that was scalable that would allow you to do that. So that's what we did. We created the WormBot. It's a robotic system combined with artificial intelligence and repeated imaging that automates the C. elegans lifespan experiments. I tried for a while to get academic funding to do this. Again, it's really hard in academia. I talked about, the hallmarks of aging and limiting the scope. It's also very hard in academia. NIH scientists have been trained not to fund anything that isn't a sure thing in their minds. And that means the work pretty much has to already be done. So when you propose to do anything that's unbiased, you get labeled as doing a fishing expedition. It's a fishing expedition. You can't fund that. That's the criticism. And that's kind of a death knell. And, my view is you're never going to catch any fish if you don't go fishing, but reviewers don't respond to that. So I realized pretty fast it was going to be a challenging road to get this funded on the academic side. So we then spun out Ora Biomedical from my lab. This was about the same time I was leaving my academic position. And set that up as a startup biotech company, and have tried to get venture funding. That's also been challenging. Again, I think venture capitalists have a different mindset certainly than NIH reviewers, but they also like to see what's been done before. So they're pattern matchers, not all, but many. So it's been challenging. So it's been slow, but Ora has the technology and has been using this technology to allow for very high throughput longevity intervention screening. I think the data set at Ora now is on the order of 10,000 plus interventions that have been screened. It's enough to get interesting hits for sure, combination hits that are synergistic and additive, which makes sense, but we really haven't explored as a field. We have an mTOR inhibitor that's probably twice as effective as rapamycin, which is interesting. So it's very early stage. What I would love to see happen, and honestly, I shouldn't say this because the guys at Ora are probably like, come on, you're a shareholder. I don't care if this is done in the for-profit or the nonprofit sector. I think as a field, if we had a database of 1 million interventions and their effects on longevity and health span, even if it's in worms, and we could just give that data away, that would have a huge impact on both the state of knowledge about biological aging in the field and give us leads to pursue. Right now, again, it's really interesting to me, the people who are very excited about the pipeline in longevity biotech. There is no pipeline in longevity biotech that we don't already know about. It's like mTOR inhibitors, metabolic activators.
Yeah.
maybe senolytics, right? So that's a little bit of an overstatement, but the reality is there are not a lot of paradigms for interventions that people are seriously looking at that are very far along, that aren't preclinical at this stage. And even when you look preclinical, it's a handful, 7, 8 modalities people are looking at. What are we missing, right? So I would just, and it would cost $5 million. Like, that's a drop in the bucket compared to what we throw money at in this field. Like, to me, this is a no-brainer. I feel about this the same way I felt about the dog aging project in 2014. Like, this is obvious. Yeah. What are we doing? Let's step up and do it. So that's Ora Biomedical, but that's also my sort of plea to, like, somebody wake up, for fuck's sake. Sorry, I'm going to swear again, but I'm passionate about this. Like, this is important.
We have to check, use the,
you can bleep me out.
The check mark for the explicit content in this one.
But really, to me, this is like, it's important. It should have been done. We would have hundreds of thousands of interventions today if we had funding 2 years ago. Like, it's not even a long time frame to scale this thing up. So come on, let's do it.
Related to this maybe is the incredible hype and hope people are putting on artificial intelligence now.
Sure. And
how that might speed up the process of finding interventions. How do you view that right now?
Yeah, so I would say there's reason for hope, for sure. I think when it comes to finding new interventions, I'm less optimistic than I am about other ways that artificial intelligence can accelerate progress in the field. The reason for that is the approaches that I've seen so far all rely on using artificial intelligence to predict new interventions based on the interventions we already know about. And this gets back to the very narrow lens that we've studied the biology of aging through. Like, if you give the neural network rapamycin and metformin, guess what you're going to get out? Things that look like rapamycin and metformin. That seems obvious to me. And that's what we've gotten so far. So I think what we need is a much larger training set. That's actually one of the most powerful features of the million molecule challenge, as we call it, for Ora Biomedical. If we had 1 million data points we could give the neural network to look at combinatorial interactions of different drugs and individual interactions across a whole host of targets, I think the insights you're going to get are going to be much richer from that sort of an application of AI than what we can do today.
Isn't that a fantastic selling point for Ora, though?
You would think so.
We can get you the data you need to train your models.
Yes, you would think so. Again, I'm just going to leave it at I'm frustrated currently. But that's not new for me. There's always something I want to do that I can't do because I don't have the resources or the bandwidth. So anyway.
But you think AI could be playing an important role right now in other areas?
Yeah. So again, I think the obvious use case in the basic research side where there's clear application and it's already, been impactful is in biomarker discovery. As we get more longitudinal data from humans that includes genetic data, multiomic data, survey data, right, where we can get a comprehensive picture of people, start to create some of these digital twin models. Those are still rudimentary, but the concept is there. I think that that's one place where AI has had an impact and will continue to have an impact going forward in being able to integrate all of those diverse data types and identify patterns that we wouldn't be able to identify otherwise, for sure. And then the other place that, where we and other people, we at Optispan and other people are already, using and exploring AI is in clinical practice, right? So again, there are many ways that, especially the large language model tools that have become so powerful recently, can have an impact in clinical practice, both in terms of helping to integrate and digest a diversity of data types that we can get from existing diagnostics. So imaging, again, patient survey or transcripts of conversations with patients, blood work, DEXA, physiological measurements, physical function, things like that. Integrate that data and then report it back to a physician or even to a client in a way that helps them understand the whole picture more easily. Good doctors can do that today. Good doctors who are trained in proactive healthcare, I would say, can do that today. First of all, that's a minority of medical professionals that are out there, not because they aren't smart enough, they just haven't been trained that way. But it takes a long time. The AI tools can greatly allow physicians to scale if they know how to use these tools. So that, to me, that's already happening. That will happen. That, to me, and those tools will get better. Again, I think early on, there was concern about mistakes. There should always be concern that the AI's tools are going to make mistakes. I think those concerns have started to become alleviated because of how the later generations are performing now. Not to say you don't want to fact check the LLM, you do, but they make a lot less mistakes than they used to. And a good doctor can who knows how to use these tools can greatly reduce the likelihood of any real mistakes making it through to the patient.
I guess misdiagnosis is a big problem without
yeah, but human docs
AI.
misdiagnose. Yeah, right, exactly. That's what you were getting at. Yeah, I think this is where I think if we weren't humans, we could take a purely logical view of this and ask the question quantitatively, are mistakes made more often when humans are in the loop, solely in the loop with the AI, or completely out of the loop? That's a hard thing for us to do. And just look at self-driving cars, right? That's a perfect example where even when the self-driving cars can perform from a statistical perspective better than human drivers, we don't want to give up the control and we fear the self-driving cars. So that's a human psychology piece that we're just going to have to deal with. But you're right, mistakes happen all the time when AI is not in the system. And I think AI, when used properly, can help reduce those mistakes for sure.
Yeah.
And my big optimism there is that I think as there's a greater appreciation for preventative and proactive healthcare, if the AI tools are integrated well, that is an opportunity to alleviate some of the healthcare disparities that exist. Because a big part of the expense of doing this sort of proactive healthcare is in the doctor time and the physician time and the other medical personnel that are involved. If AI can help scale those people, so instead of seeing 10 humans, they can see 100 humans, that will help with costs and hopefully make that kind of care more widely available, which in my view is, from a public policy healthcare perspective, where we absolutely need to go right away, because at least in the United States, our healthcare system is imploding and it's not sustainable the way it is. This is an opportunity to create a sustainable healthcare system. So that, I think, we'll definitely see the AI tools become much more prevalent there. And I'm pretty optimistic that will be relatively smooth. It's not going to be a perfect integration, but I already see, positive movement there.
I guess this is a good way to talk about your other company, Optispan. Mm-hmm. You mentioned proactive healthcare, and I guess that's what you're doing with Optispan. For a lot of people, Optispan might be your podcast, but right. I guess for you might relate it more to the clinic. Yeah. So tell us about Optispan. Really. Yeah,
I
a
would say. Yeah.
platform. Yeah,
I mean, the
you
way
can explain what it is.
Sure. Yeah, the way I think about Optispan is we are a healthcare technology company first and foremost. We are a healthcare technology company that has clinical programs and has a podcast. So our overarching goal is really to enable this kind of science-based proactive healthcare for as many people as we can, right? And that's I get that's a big concept. It's sort of nebulous. What does that mean? And so within that, we believe that one of the things that we can help with is to create the technology, the infrastructure for what does best-in-class health span medicine look like. And I'm using that phrase health span medicine mostly because I feel like already, unfortunately, longevity medicine has been tarnished in a lot of ways, in a lot of people's minds. But we're talking about true longevity medicine and health span medicine. The idea is to use the best tools that are currently available to detect problems early and help people get onto a better health span trajectory so they can maintain high function as long as possible. Some of that is about the biology of aging, but of course, some of it is about traditional healthcare. A lot of the biomarkers that we know are predictors of disease or pre-disease, and moving people away from the trajectory towards disease or detecting disease as early as possible. So a lot of what we've been doing the first 18 months is we set up the clinical program first because I very much felt like I needed to, because I haven't been a clinically practicing medical doctor, right? I needed to understand what are the friction points within the healthcare system and how do we navigate that? And what can we do that's affordable and realistic and that people will do? And how much of this is going to be about trying to modify behavior? Because of course, lifestyle is the most effective way to maintain health, right? And how do we go about that? So we created these clinical programs early on for that reason. And we've learned a lot. I have learned a lot. And now we're starting to turn the page and really try to develop the computational infrastructure to support those clinical programs. So I feel like we have dialed in generally what we want to do. If you have a very high-end concierge clinical practice, what can you do? What's effective? How do you communicate that to doctors and patients in a way that helps them get to where we want them to get to? And then at a sort of next tier down, what I call the health span 80-20, right? If you only have 20% of the resources, can you get 80% of the benefit, right?
Right.
What can we do at that tier? And we've got that more or less figured out too, I would say. And now how do we operationalize it? How do we create a scalable way to give this information and the tools to medical professionals, maybe someday directly to patients, but at this point, I have no interest in going direct to consumer, and we can talk about why. But how can we scale this in a way that makes it easy for folks to adopt and that they want to adopt, right, into their practices? So that's what we're building now, is that computational data, technical infrastructure to do that. And then, as you can imagine, or maybe you can't because you haven't been through it, but there are a lot of moving parts that go into trying to navigate the way the healthcare system works, the way healthcare vendors work, the way data privacy works. Like, it's complicated, it's messy. There are reasons why our healthcare system is so dysfunctional that go beyond the insurance companies. I mean, the way insurers support healthcare in the United States is problematic, but there are far more prevalent institutional problems with the way healthcare infrastructure works and hospital systems work that also are challenging. So figuring out what we can do and what we can't do, I think, is also, part of the learning curve here.
I think that's so important because you mentioned the 80-20 method here.
Yeah.
Because I think that a lot of so-called longevity clinics or longevity medicine or whatever you want to call it, they kind of stay on that concierge path. Right. And so people are like, yeah, but what about me? I can't afford. Yep. I can't afford it. And I've kind of criticized that a little bit because I think that speaks against the whole idea that we longevity should be for everybody and so on. So it's really interesting to hear you talk about what can we do for the rest of you.
Yeah, no, I align 100% with that perspective. I do think, it is also important to recognize that there are business incentives that cause most people to go down the path of only serving very, very rich people, right? So I don't want to, I personally am not going to criticize medical providers or people who open these clinics, and the price point is $50,000 or $100,000 a year. There are reasons why they believe they have to do that in order to be successful from a business perspective. We'll see if we're successful with our model, right? And also, I will say, I do tend to criticize some of these companies that go direct to consumer, not because I think direct to consumer is a bad path to go. I would love to be able to offer our programs directly to consumers. That's hard to do in the United States because of the way healthcare is regulated. And it's hard to do because the incentives in the direct to consumer market almost force people to do things that are dishonest, in my view, in order to be successful. So what I mean by that is, if you want to be one of these companies that sells blood tests, let's just say, right? You want to sell blood tests. We could do that. I could tell people right now, and I do tell people right now on our podcast, what should you measure, right? We could tell people what our blood test is, make it available online for consumers to buy, and not provide any interpretation for them, not provide any healthcare, because if we provide healthcare, then that gets complicated and expensive, right? But if we just sell blood tests and give them their report and say, you know what, here you go, take it to your primary care doctor, I don't think that's helpful for most people, because their primary care doctor doesn't want to deal with that, right?
Yeah.
And so what it does is then they put it into ChatGPT, and then they start trying to interpret their own medical data. And again, ChatGPT is not bad. I'm not even critical of that. Guess where I put my blood work when I get it back first before I talk to our docs? I run it through ChatGPT. But if you don't know, if you don't have the nuance and the insights to really understand what you get back, it creates, in my view, oftentimes more problems than help. But that's the way the incentive structure in the diagnostic direct-to-consumer testing space is set up. That's why people do it that way. And then there are the companies that sell other types of diagnostics that are not validated or regulated in any way. And there I would put the biological age tests, where we have no information about precision or accuracy other than the information that people like me who do our own self-experiments provide. And yet these things are presented as if they are giving people accurate measurements of biological age or mortality risk or disease risk, right?
It's very prevalent now.
It's very prevalent.
Yeah. It's kind of like an established truth because so many people are talking about it, and there are these Olympics and all kinds of things, but still they're not reliable, right?
So here's what I would say: they are really useful research tools when used properly, right? And I think they certainly, when used properly, can have correlative value for likelihood of dying within the next 10 years or 5 years, and correlative value maybe, I mean, it's early days, but probably for specific tissue and organ functional metrics. Like, it might be able to predict, is your kidney having a problem and the rest of your body is okay right now? That if those things were to be reliable, and we knew that they were reliable, there's value there. So I am very bullish on epigenetics as a technology for predicting outcomes. And we use epigenetics in our clinic for multi-cancer detection, right? So I think there's a lot of potential there. The problem is that these companies that rush to market, the direct-to-consumer market, aren't regulated. There's no incentive. I mean, I'm not saying they aren't doing this to the highest quality. Actually, I am saying they aren't, because at least the ones I've tested aren't, and I have data to back it up. But that doesn't mean they couldn't be doing it to the same quality that you would get in a peer-reviewed research paper, where you have to do triplicate replicates and show, variation and know what the technical variance is. They aren't doing that. And they are making claims that are dishonest. They are telling people that this is measuring biological age. It's not. It's a correlation to biological age. And so people are being misled, and that's problematic. Where I really, though, see a problem right now is when medical providers, physicians, longevity docs are recommending these biological age tests. To me, that is irresponsible. This is a provocative word, and I don't mean malpractice in the sense they should be sued for malpractice, but that's medical malpractice. A medical provider, in my view, should never use a test, number one, they don't understand. A few docs understand these tests, the vast majority don't. You should never use a test where you don't know the precision or the accuracy of the test, or at least you can find that information if you need to know it, right? We have no idea what the precision or accuracy of these tests are. And you should never use a test that's not actionable, that doesn't inform clinical care. Getting a number of biological age is not actionable. So to me, it's irresponsible for medical providers to be recommending and using these tests for those reasons. And I know there are people who disagree with me, but I've never heard anybody disagree with me and actually give a rebuttal to those three things that I just said, right? So it's frustrating. And I would like to see longevity doctors who are using these tests be more thoughtful and rigorous and responsible in the way they are caring for their patients.
Something that actually surprised me, maybe I shouldn't have been surprised, but I was that you personally took a therapeutic plasma exchange.
Oh yeah, TPE.
So tell us a little bit about what that is and
Sure.
why, because it feels like you are optimistic about that procedure.
Yeah. So happy to talk about that. A couple of things that are worth saying. So therapeutic plasma exchange, first of all, for people who may not be familiar, is just a process where you have two IVs, one in each arm. Your plasma goes out one IV. It goes through a machine that has a centrifuge. So the cells are spun out. The blood cells are spun out. The plasma is collected. The blood cells then get resuspended in a saline solution with albumin, which is a protein in blood. And then it comes in the other arm, right? So it's replacing the plasma, about 80% of the plasma in one sitting. Okay, so a couple of things to appreciate. It seems really edgy. Like it seems like, oh my God, Matt's doing therapeutic plasma exchange. It's an FDA approved procedure, right? So this is no different in one context from off-label use of rapamycin or metformin or any other FDA approved drug. This is a safe procedure that has passed all of the FDA safety requirements and efficacy for certain indications. It is being used off-label for potential benefits for longevity, and particularly where I found the data intriguing for benefits in people who are at high risk of cognitive dysfunction or dementia. I'm not, at least as far as I know. I don't have any genetic predisposition, and I don't think I'm experiencing much cognitive decline. But the data there looks pretty interesting.
Certainly doesn't seem so.
Well, yeah. What I always tell my wife when she gets on me about my cognitive function, I'm like, yeah, but I started up here, so no, down here. No. But what's also interesting to me is there's a lot of, I think, appropriate thought being put to environmental toxins, right? Heavy metals, microplastics, things like that. That's the place to me where therapeutic plasma exchange seems intriguing. It is absolutely going to be the case that if you take out 80% of your plasma and you put in clean saline and albumin, you are going to reduce the levels of circulating metals, circulating microplastics, if you have a high level. I'll actually talk about that because I think that's interesting. And even if you have high lipids, that's one of the uses of TPE in people who have very, very high lipid levels. So familial hypercholesterolemia, you can reduce lipids. Now there you have to do it much more frequently. So the idea is that makes a lot of sense to me. That's definitely going to be effective. How beneficial is it going to be? That depends on you and your levels of toxins and your levels of microplastics and all that. But it's going to have that effect of diluting those out. And then what are the risks? Infection. Anytime you get an IV, infection's a risk. There's not a lot of risk beyond that. And the way that the company I did the TPE through does it is they also put in IVIG, so immunoglobulin, to sort of boost immune function afterwards. I don't know how big the effect there is. Anyways, so that's why I did it. I went to a conference where I heard a talk by Dmitry Kiprov on some of the data they had collected on cognitive function, which I think now has been published at least as a preprint, and therapeutic plasma exchange. It looked pretty compelling to me. I went and did my own research afterwards. I'm like, okay, this seems like an interesting thing. And I reached out to Brad Youngren, who's the CEO of a company called Circulate. Circulate puts these machines and the personnel into clinics who then offer TPE. And so he said, yeah, we got a clinic in Seattle, and we met and hit it off. And I'm actually, full disclosure, I'm on the scientific advisory board for Circulate right now. And so I went and did it. And, I'll say I didn't feel like, it's not like the rapamycin with the frozen shoulder. I didn't come out of it like, I feel great, I'm Superman. I didn't really feel anything. One way or the other. It was an easy experience, except you have to sit still for 3 hours, which for me, I'm kind of a fidgeter, was challenging. But otherwise, it was an easy experience. I did have my microplastics measured before and after. Good news is I had essentially no microplastics before. I was at 1, and the assay goes from like 0 to, I don't know, 5,000 or something like that. And I had 5 afterwards. So is that a real difference? I don't know. There is some evidence that just the tubing from the IV can actually put some microplastics back in. So maybe I increased my microplastics from 1 to 5, but I'm so low, doesn't really matter, right? My lipid levels went down a bit. I do have my lipids, historically have been sort of my LDL, especially a little bit concerning, ApoB a little bit concerning, not like, oh my God. And I've actually done CCTA, so I know what my soft and hard plaque burden is, but my lipid levels went down a little bit. Probably not going to be persistent. I'm sure they're back up by now. In fact, I know they are because I just had a blood test. But I can't say there's anything personally that I experienced where I'm like, yep, I'm convinced about TPE. It was easy. It's still biologically plausible to me. I don't know that I would have expected anything profound given that I'm in pretty good health. So I'm still bullish on it for certain uses.
Yeah. As you were doing it or immediately after or something like that, there was this paper coming out, right? From Buck and Circulate. That actually showed, we talked about biological age.
Yeah, right.
They showed a lower biological age with different clocks.
Well, no, what they showed is a decrease, a change in the methylation pattern that is consistent with reduced mortality, right? So I get why people use the shorthand biological age. They did not show a lower biological age. You can't measure biological age. People should never, and I'll give them the same grief I give everybody. No scientist should ever say in a peer-reviewed publication that they measured biological age. They didn't. That's bad science, or at least it's bad science communication in my view. I get why if you're an influencer on a podcast, fine, you can talk about biological age that way. This is part of the reputation problem I'm talking about with the field. That kind of sloppiness is seen by the rest of the scientific community. I mean, could you imagine if cancer researchers had, in their title that they cured cancer in every other paper? Like other fields don't do that. We need to be better.
But Matt, I don't know. We've been going on now for almost 2 hours. We could probably spend 2 more hours, but we won't take that time away from you. It's always fantastic. What we always do is we ask our guests to recommend 3 books.
Sure.
And have you thought of any that you would like to recommend to our audience?
Yeah, absolutely. So I mean, I'm gonna mention 4 because there are 2
You're that entitled to mention 4.
So for me personally, I think in the longevity space, I typically don't read books in the longevity space in part because I know most of the science, and it frustrates me when people get things wrong. One book in the space that I do recommend to people is Peter Attia's book, Outlive. I think that is, in my view, a really powerful and good example of science communication, and the communication around the importance of being proactive about your own health. So if people haven't read that, that's a great book, and I recommend it.
It was it was on Peter Attia's podcast that I first heard about you.
Yeah, right. I've been on Peter's
6 years ago or something like that.
Peter. Peter, I really appreciate Peter both as a person and for what he does in terms of communicating the science and the importance of the science of longevity. The science book that had probably the biggest impact on me very early on was Stephen Hawking's A Brief History of Time. I know it's an older book now, but for me, that was one that really, I think, ignited my curiosity about science and the universe. And then 2 books that have a very personal meaning to me is actually I've got them right behind me. If you look on my podcast, you can actually pick these books out. So one is The Man Who Saw Seconds, which is written by a friend of mine, Alex Boldazar. It's a science fiction book. I won't give it away, but it's a great read if you like sort of mind-bending science fiction. And there's a lot of physics in there. There's even some biology in there as well. He actually just won the Locus Award, which is one of the major science fiction awards. So that's a great book. And then my wife has written her first book that's published.
Oh, wow.
This is about her trek to the Everest Base Camp. So her name is Tammy Kaeberlein. I love this book. Of course, I love my wife very much, and I see her in the book, but I think people will enjoy it. She has another book that will be coming out soon. So this is about, like I said, her trek to Everest Base Camp, if you want to know what the book's about. It's called Mountainside. She has another book coming out soon, it's a fiction book, but it's based on her life growing up in Alaska that has, I think, some really powerful insights into what it's like to grow up in an environment like Alaska, which is a very unique place to grow up.
It seems like a place like nothing else.
So that'll hopefully be out in the next year. That book is amazing. I highly recommend it. Yes, I'm biased, but she's a great writer.
Perfect. Hope she will take a look at this episode.
Yeah, I hope so too.
It would be good for you.
Or maybe not. Sometimes I get feedback on some of the things I say. It's like, did you really say that? No, she's great.
Yeah, you did use the F word a few times.
I sprinkle it in here and there for impact.
Thank you so much, Matt. And
you're more than welcome.
You're always welcome back.
Great. Good to see you guys.